In a previous video, we talked about how to generate simulations using random number generation in Excel. We talked about the rand function and how it's a uniform distribution with outputs values between 0 and 1, a continuous uniform distribution. We also have talked about the rand between function, which outputs integer values between a range of values, again, uniform distribution. And we've talked about how we can use the rand function in combination with the normal inverse function, for example, in order to generate simulations of data related to the normal distribution. Now, we can certainly do that, and we can do that for other kinds of distributions too. But what I want us to look at is a built-in function in the Data Analysis Tool Pack that can do all of this with pointing and clicking instead of kind of remembering how all of the different functions work. So let us experiment in our Data Analysis Tool Pack with the random number generation function. If we click OK, we get a pop-up screen that gives us a bunch of information. I am going to change my output range to be somewhere on my first page. And let's look particularly at the distributions that are available in the random number generator tool pack. So we've got a uniform distribution. This function basically is going to replicate the rand function. So how many numbers do I need? Let's say 10. We'll come back to this random seed in a second. And it outputs 10 functions, 10 numbers, basically just like the rand function. Again, these will be different values, but the rand function generates values that basically work the same way. Okay, so that's the random number generator for the uniform distribution. Now, also an option here is the normal distribution, and we use this a couple of times when we were generating residual errors in our regression coefficients video. I've used them to do simulations of like test scores, like SAT scores and other videos. We can do these to generate all kinds of normally distributed variables. If we click on it here, it's going to give us it's going to ask us for the kinds of things we put into the norm inverse function, which is the mean and the standard deviation. So let's just illustrate, for example, let's suppose I wanted to calculate the mean height, some examples of the heights of women. Women tend to be on average about 64 inches with a standard deviation of approximately 3 inches. And I'm going to put my output range right here. And I'm getting a number of random numbers. I'm getting 10 generated from this distribution. And here, again, the random number functions are going to update. Don't worry about it. The ones that are built from the formulas are automatically going to update. The ones that you build from the random number generator are going to be calculated and then fixed in place. So they're not going to update. We could generate these same kinds of values from norm.inverse with the rand function as the percentile, essentially, mean of 64 and a standard deviation of 3. And again, we produce values that follow the normal distribution with the same mean as standard deviation. It's just, but again, one of the differences here, we don't need to remember the whole function. We don't need to remember how this goes together. And we get fixed values. These are just numbers that are output from the random number generator function. These are formulas that every time I hit an enter function are going to keep updating. And so I have to copy and paste the results as values in order to get them to stop updating. So let's label that. Let's label that. Now, we have other options that we can use that I haven't experimented with in previous videos, but those are not the only possible outcomes that we could get. So for instance, a Bernoulli variable is a variable that is either 0 or 1. And the chance of getting the 1, the success, you would specify here. Let's say we could do it like a coin flip, right? And then let's place this someplace right here. And we'll get 10 of them. So like 10 coin flips. Now, how did we do this when we were doing this before? When we were doing our dice experiments, what we essentially said was we did a RAND uniform, and we said if it was less than a particular value, then we'd get a success. And if it was greater than, we'd get a failure. So we can regenerate, we can reconstruct this idea that we're doing essentially a sample coin flip problem by using the random number generator with the Bernoulli variable, or we can use that if statement with the rand function and set the p-value to be where it flips, where that break is, where this is 1, this is 0. Now, that's fine for one example of one coin flip of 10. But what if we wanted to do this over and over and over again? We wanted to do 10 trials of 10 coin flips or 10 trials of 20 coin flips. Well, we could do that. We could build our table. We could have columns of all of these things, add them up. But in our random number generator, we can actually select binomial, specify our p-value, and you can put in a % here if you want, and then the number of trials in each of our variables. So I'm going to change the number from 10 just so that it's not 10 of everything. Let's say we want to do 15 coin flips. And then where am I going to put this? I'm going to put it there. And so now I've done a fair coin. I've flipped it 15 times. I've counted the number of heads, number of successes. And all I have is the counts now of the successes. I don't have the raw data. I don't have the columns and columns of ones and zeros. All I have is the output. And again, there's ways that you can do this as well using the binomial distribution and even the Bernoulli variable function, but this is much faster. The Data Analysis Tool Packl has other distributions in it, which you may or may not have covered. The Poisson distribution is a distribution that essentially is used for counts of things that follow an exponential distribution. Sometimes they're referred to as a Poisson process. Typical examples are things like the number of atoms that decay in a second in a uranium mass, or the number of people that go through a drive-through in an hour at a bank. So it's a counting process, but the events are not equally spaced. And so there is a time component. There's a certain probability there will be events that happen after a certain point of time. And the number that you have to specify, this lambda value, is essentially the mean. So let's say I want the number of people that are going to come through the drive-through in the next half an hour, and the mean value is 5. And then I want to simulate what happens on 5 successive days at that same window of time. And let's put my outcomes here. And so this is my Poisson process. The mean is 5 people, but sometimes I get more than 5 people. Sometimes I get fewer than 5 people. Sometimes I get exactly 5 people. And there's a probability distribution that goes with this. Now, patterned is a little bit more complicated, and we're just, I'm going to show it to you, but I'm not going to run it because I've never actually come up with a reason to use it. But the parameters are, you give it a range from, let's say 1 to 100 or something like that, and you give it a certain step size, and then repeating each number so many times and repeating the sequence so many times. So there's a pattern to the data that you want to try to replicate. Again, this is not something that we have in statistics very often. The thing that immediately comes to mind to me is like trying to generate random music, but it's something that is worth experimenting with if you want to play around with your random number generator. And then the last one is discrete. And to run the discrete one, you need to input a set of probabilities and values. So before we run this, we actually have to set up a list of values and probabilities. So let's say 1, 2, 4, 8, 16, 32, and probabilities. We want to make sure that these sum to 1. So I'm going to put my checker out here. So let's say 0.1 and 0.2 and 0.3 and 0.2 and 0.1, and then we'll also have 0.1 or 0.1, not 1.2. Yeah. Okay, so they add up to 1. So this is my range of values and probabilities. So now let's go back to my. Now the idea of the discrete random number generator here is that you are going to specify the outcomes that are possible and their likelihood. So value and probability input range. And then we're going to output it right here. Now, again, this is something you can do with a rand function if you set up a fairly complicated if statement. Oh, it doesn't like it. It wants it in columns and not rows. All right. Let's reconstruct this. See, sometimes you don't know until you try it. X, 1, 2, 4, 8, 16, 32, and E of X, 0.1, 0.1, 0.2, 0.3, 0.2, 0.1. Sometimes these things have quirks. All right, let's try that again. There we go. So, woo! So what it did is it looked at these probabilities and it basically picked a random number function, and then it determined what that random number generator, that again, I'm using the rand function behind the scenes, where that probability fell, that value that they came up with fell on the distribution, and it output the value. And then they did a new random number generator from the rand function, figured out where that fell, output the number, and so on and so forth. And what we end up with this is a list of values that are taken only, not just any number from 1 to 32, but only these specific 6 values from 1 to 32. And then again, if you were to do a whole bunch of these, they would have the approximate distribution that we've described here. So these random number functions are really kind of cool. And I wanted to show you one more thing. One more feature, and that is the number of variables. So let's say I want 3 of these. So then I'm going to actually, I don't want to overwrite it. I want to put it next to it. And so now it redid that same process, whatever process we had selected, it redid that same process using my probability distribution that I described earlier, but it regenerated another set of 10 random numbers, and it figured out where on the distribution it fell and output the corresponding value. And it did it 3 times because I specified the number of variables to be 3. Now, the one other thing that I wanted to mention that isn't available in this particular example, but is in some of these other ones, is this idea of a random seed. Now, sometimes when we're doing simple random experiments, we don't care about being able to repeat the same values that we got again later. But sometimes in science, it's important to be able to replicate our simulations. And in those circumstances, we can put a random seed in here. The Excel, of course, uses a pseudo random number generator in the background to generate these random numbers. But so that you can, because it's a formula, it's an iterative process, you can tell it where to start. And by putting in a value here, it doesn't matter, you can pick a value. Some people pick their birth dates. Some people just pick 0, but you can pick any number you want here. But what it's going to do is that every time you run the pseudo random number generator, if you start with the same seed, you're going to be able to replicate the output. Now, if you don't have a seed here, then every single time you run this, it's going to be different. But if you put in a seed here, then somebody else comes along and sets up the same exact output and then puts the seed in there, then they're going to be able to get the exact same numbers that you get. Now you can do this outside of the random number function. There is a function called seed, which you can set. In fact, didn't like that. In any case, there's a function that you can set to specify, and I don't remember what it is right now, but that you can set in order to make sure that you, again, have that replicability. But the Data Analysis Tool Packl has that set up as an option for you. Again, it doesn't necessarily work in every single one of their random number generator functions, but it does work for like the common distributions and things like that, where they're so that you can make sure that when you repeat the same simulation, you can get the same values. They're not just close, they can actually be exactly replicated. I don't like setting the seed because I really want them to be random, but I'm not trying to publish in the scientific paper my examples either. So, but that's an option that's available in case you need it.